In this video, we're going to talk a little bit about contour diagrams and do a couple of examples related to those. So what is a contour diagram? Well, it kind of provides us another way to represent three-dimensional functions or three-dimensional graphs. And specifically, the way that it does this is by taking a bunch of cross-sections and then putting them all on the XY plane. So let's look at what that kind of looks like specifically. So contour diagrams show cross sections of multivariable functions at different heights. Okay. So if we have a multivariable function, we can say something relatively simple, like say z equals x squared plus y squared is a really nice one. So this one's actually pretty straightforward to draw. It's just a parabola that kind of sweeps around like so. And another way to represent this, though, would be to take cross sections of it and collect them onto the XY plane. And so, well, what does that really actually mean? That means that we are pretending what happens when we take a plane, say the plane z equal to 1 in this case, is what I'll draw here, and then asking ourselves, how does that intersect our three-dimensional shape here? Well, in this particular case, it's going to intersect the paraboloid in a circle, like so. And that provides us the cross section that we would then put on the XY plane. So we can draw this over here like so. In this particular case, this has a radius equal to 1. We would put a circle on here like this. And this corresponds to the height, z equals 1. Okay, so, well, the idea of a contour diagram, though, is that we don't just stop here. We're actually able to put multiple of these cross sections onto the same XY plane. So we could take a cross section at, say, z equal to 2, which would then give us a circle of radius root 2. So it's going to look something kind of like this. Or we could even kind of go back down a little bit and look at the base here, right there, and what that cross-section looked like. Well, any plane that we put there along it's actually just the XY plane that is laying right there, that's just going to intersect at the point. So that's what we have at z equal to 0. So that's just kind of like a quick idea behind what these look like and where they come from. But a lot of times, I mean, we don't really want to graph a three-dimensional function and say, okay, let's imagine what the planes look like as they intersect it and then draw it that way. So how can we do this without ever really having to work with the three-dimensional graph? Well, the secret to this is to note that the big idea is that we're setting z to be equal to a specific value. So you always start by fixing a value for z. And then after that, you're left with a specific function just in terms of x and y. So you graph the leftover function. And then you just do this over and over again for evenly spaced values of z, or z. And this one right here is actually really, really important because as long as the spacing between z is the same, we then know that tighter contours imply greater rates of change in the graph or more steep graph, right? So be sure to pay careful attention to this. But you can only say this idea of closer lines implies a steeper graph, if you know that the values of z that are being used are evenly spaced. So be careful with that. So let's work an example. It's just going to be kind of like a modification of what we just kind of looked at. We're going to take z equal to 4 minus x squared minus y squared. And this one, I am going to go ahead and draw the graph just so we can kind of keep track of what we're doing. So this graph is really just a paraboloid that has been flipped over and then shifted up 4 units. So it'll look something kind of like this. And for this one right here, we're going to draw the level curves. It's another word for the contours for z equal to, let's say, -1, 0, 1, 2, 3. And then I'm actually going to end at 4 because that's the height of our shape here. Okay, so in order to be able to do this, all we do is just we'll start with z equal -1. And we take this value and plug it into our function for z. So we get -1 is equal to 4 minus x squared minus y squared. And then we can rearrange this to make it look a little bit more like a function of x and y that we're more used to working with. So in this particular case, we can rearrange this and get 5 equals x squared plus y squared. And this is just a circle centered at 0, 0 that has radius equal to the square root of 5. Okay, so let's go ahead and draw our xy plane so we can start graphing these things. 1, 2, 2. Okay, so for z equal to 1, I guess I can do this one in pink. I'm going to color code them because I have a feeling that once I kind of start drawing these on here, it's going to be tough to read the labels that I put on. But for z equal to 1, r is equal to root 5, and square root of 5 is actually more or less 2.2. So that's kind of where I'm going to wind up putting this guy here. He's going to go just like so, and it'll be this circle. Okay, so that's our first contour, and this goes for z equal to -1. And if I wanted to look at see what this would be on here, that's kind of more or less corresponding to, so if that's -1, this band that comes right around like so. Okay. So let's do our next one, z equals 0. I guess I'll color code that like so. So what this means is that we have 0 equal to 4 minus x squared minus y squared. So you just wind up with 4 equals x squared plus y squared. So this is just a circle centered at 0, 0 still, and then this time our radius is just equal to 2. So we can graph this in green, and circle radius 2 with center at 0 is going to look like this. So that's z equals 0, not 2. I wrote 2. Z equals 0. So we can do this again for z equals 1. And in this case, we just get 1 equals 4 minus x squared minus y squared. And then rearranging that, you're going to get 3 equals x squared plus y squared. So you have a circle centered at 0, 0. And this time, r is equal to root 3. And root 3 is more or less 1.75-ish. So let's graph that one we set in blue. So 1.75 is going to land us just above half. It's going to put us right around there. You can kind of see how as we're getting closer and closer to moving in toward the origin here, our circles are maybe slightly spaced out, although I guess it could be kind of tough to tell with the way that I've drawn them. But you'll see they'll get more spaced out as we keep going. But that's kind of what's happening here, though, if you keep track of the way that that's sloped. So that corresponds to the height z equal 1. And I guess I've kind of forgotten to track back to what was on here. Z equal to 0 would be something kind of like that. Z equal to 1 would correspond to this stripe here. All right, so our next one is going to be z equal to 2. And we're going to have the same idea here. So I'm just going to write out that we wind up with the circle 2 equals x squared plus y squared. And this means that our radius is equal to square root of 2, which is about 1.4 in that case. So it's going to be just under 1/2, or 1/2. 1.5 is where we're going to place this circle. This is kind of a lumpy circle. But this corresponds to z equals 2. So that would be more or less this stripe right here. And then next we have z equal to 3. So we have 1 equals x squared plus y squared in this case. So that's just radius equal to 1. So that gives us this circle here. And then looking back at our original graph, that's this piece. Okay, and then our final one is that z equals 4. And for this one, we're going to get that we wind up with 0 equals x squared plus y squared. And this setup right here, since both of these pieces here have to be positive, it means that x and y both have to be equal to 0. So the only option for that particular one is just going to be the point there at the origin. And that kind of makes sense because our graph comes together at a point at the very top at z equal to 4. So that's pretty much all there is to this one. Again, I want to kind of point out, and some of my circles are kind of lumpy, so maybe in some places it's not quite as easy to tell, but you can kind of see how the graph becomes steeper the farther and farther down we go. And you can see as z approaches -1, our circles become gradually closer and closer together. Or you can think about it the other direction, as we go up towards 4, it becomes a little bit flatter and it starts to flatten out before it tips over and starts going back down. And that's kind of reflected here, where we have these circles that are getting a little bit farther and farther apart, especially here going from this z equal to 3 circle into z equal 4, that point there in the middle. There's quite a bit of space there. And I also just want to kind of highlight, though, that when we're working with a contour diagram, a lot of times you'll see that along these same lines, that a maximum or even like a minimum will be highlighted on a contour diagram in that it's kind of the middle of like a circle or a bunch of rings or something. So just something to kind of watch out for when you're working with that. One more example. This one looks a little bit different, and I'm not actually going to draw the 3-dimensional picture for this one because this one's a little bit more difficult to draw by hand. So I'm hoping that that kind of highlights the utility of working with contour diagrams instead of having to work with the 3-dimensional one. But I do still want to give you an idea of what this looks like. Anytime that you see like a squared on one of these terms, you should kind of think, okay, maybe this looks sort of like a parabola, especially when there's a squared only on one term and not on the others. So this z equal x squared kind of indicates that there's a parabola involved. And then when we add this y to it, instead of making kind of like the circular cone shape like we had in the last example, since we're just adding y and not y squared, it doesn't create the circular pattern to it. All it's going to do is create a tilt to it, or kind of slant it a little bit. It actually, if you want to picture it, it looks more or less like a taco that's been kind of tilted on one end. But anyway, we're going to kind of use this to come up with our contour diagram. But we're going to do this primarily algebraically, meaning that we're just going to go ahead and start with z equal to, let's say, -2, -1, 0, 1, and 2. So if we start with, say, z equals -2, plug that in, we're going to get the graph, or the equation -2 equals x squared plus y, which we can rearrange into a function we're more comfortable with, y equals -2 minus x squared. And this is something that we definitely know how to graph, because all it is a parabola on the xy plane that has been flipped over and then translated down 2 units. So it's a parabola. It has its base point here at -2, and then it's been flipped over. So it'll look something kind of like that. So that corresponds to z equal to -2. So how about, let's say z equal -1? Well, same idea. It gives us -1 is equal to x squared plus y, which then means that y is equal to -1 minus x squared. So that's just a parabola that's been flipped over and translated down 1 unit. Just like so. And we're going to repeat this process for our next 3 points as well. So for z equal to 0, it winds up simplifying down to just y equals -x squared. So that's just our standard parabola at 0, but it's been flipped over. We can go with z equals 1. So you'd have y equals 1 minus x squared. So our base point is here at 1, and it's just downward facing. Like so. And finally, we can look at the point z equals 2. And that one gives us y equals 2 minus x squared. So that's just the parabola, base point at 2. Faces downward. So again, I didn't have to draw the original picture to be able to do this. All you have to do is just plug in specific values for z, rearrange the leftover x's and y's into something that you know how to graph, and then graph each one of those, taking care to label each one of your lines, because contour diagrams really only make sense if we know what height on the function that these are corresponding to. So make sure that you're paying attention to label each of those, because that's what tells us how to read these kinds of graphs. So that's it for this video. I'll see you next time when I talk a little bit about working with limits of multivariable functions. So I'll see you then.